Earth is a living, breathing organism on a grand scale. From its hot iron core to the plants and animals on its surface, to the storms in its atmosphere, Earth is constantly evolving.
It's very easy to think of this as just a great big organism that's pulsing away just like I am.
Now, advanced technology is helping us discover the hidden connections between the planet and all life on it.
Both the environment in which we live, the planet itself, and humanity determine our future.
This is your world as you've never experienced it. An X-ray vision that reveals the secrets of Earth. Every so often, Earth reminds us it's got a mind of its own. For thousands of years, we thought catastrophic events were bolts from the blue. But now we know that just as a cough is a symptom of something larger going on inside the human body, volcanoes, hurricanes, and even things like disease and pollution are evidence of something bigger going on within the body of Earth. How do we know this? It all began with a surprising discovery made in the most unlikely of places. Christmas Eve, 1968, 3 astronauts on Apollo 8 made one of history's most profound discoveries.
Then Apollo 8, how do you rate?
Yeah, loud and clear, Frank.
Less than 40 hours left to go to the moon.
For all the people back on Earth,
Emerging from the dark side of the moon, they observed a planet,
now approaching lunar sunrise.
our own.
Slowly traveler from another planet. What did I think about the Earth?
It was the first time humanity saw Earth in full. The perspective helped launch a new era of exploration into the invisible realms of our planet, which continues today. Here on the plains of South Dakota, researchers with EarthScope are deploying a sensor network that's literally bringing Earth's inside into view.
This is the seismometer. It's the instrument that will actually sense the motion of the Earth. This is the device that sends all of the data over the internet. These are the final connections to bring the station online.
Once online, this device, and hundreds of others like it, streams data about earthquakes all over the world. But more importantly, it provides data that helps scientists map Earth's insides.
Seismic tomography is a little bit like a CAT scan for the planet. So if you hurt your knee and you go in for a CAT scan, they're taking a 3D image of your knee. For the planet, what we're doing is creating 3D images of how fast those seismic waves travel through the Earth.
With these images, we see the planet in an entirely new way. "3,200 miles beneath the surface is the solid inner core. Long a mystery, tomography's shown us the core's a sphere of crystallized iron, whose surface is studded with mountains. Seismic imaging tells us that the inner core spins faster than the rest of the planet. That's because it's suspended in an ocean of hot liquid metal. 1,800 miles down, the outer core harbors enormous currents of iron and nickel. Atop this metallic ocean, tomography is showing us mountain ranges on the underside of huge rock piles called anticontinents. Scientists believe these piles of stone exist in the most unlikely place: the bottom of an enormous zone of hot, plasticized rock called the mantle. Tomography indicates they funnel plumes of superheated rock up through the mantle, where they push into the thin shell of rock at the surface, called the crust. The crust is broken into pieces called plates. Moved by the churning mantle rock, Those plates rub and bump into one another to produce thousands of quakes every single day.
We always thought about the planet as being these onion shells of layers that don't play with each other. But what we're learning is that you can't take one without knowing about the other. And to better understand that, we need to know what's going on down there.
What this kind of imaging reveals is the connection events on the surface have with features deep inside Earth. We see that the Icelandic volcano that shut down most of Europe in 2010 was just the tip of an enormous system reaching down more than 1,000 miles. Under Africa, there's a plume boiling up that is slowly shearing the continent in half. Halfway around the world, we can see Hawaii's enormous volcanoes are being fed by a plume rising from an anti-continent down near the hot liquid core. Are the major events we see on the Earth's surface connected by what's going on in her core?
Earthquakes are just one part of it. Volcanoes are another part of it. Uplift of giant mountain ranges are another part. So that's all driven by motion inside the Earth.
Pakistan, August 2010. Epic floods leave millions homeless. At the same time in Russia, a heat wave sparks fires that scorch thousands of square miles. And in China, fierce storms trigger landslides that kill hundreds. Are these devastating events the result of movement inside Earth? Or is there more to the story? Some scientists believe they may be tied to climate change. But what do our sensing technologies tell us?
We like to look upon our job here as being a hospital that's looking at the Earth. And we measure the heart rate, the blood composition, and then we look at how this is changing over time.
Like the inside of the planet, the atmosphere around Earth has layers. And though they extend out hundreds of miles, most of the atmosphere is concentrated down at the bottom.
It's hard to believe, but if you fly in an aircraft at 30,000 feet, 90% of all the world's air is beneath you.
To examine the atmosphere, NOAA researchers play doctor. Just as a physician draws blood to diagnose a patient, researchers here take air samples. They're looking at the individual gases in the atmosphere to understand how subtle shifts in concentrations translate into huge global changes. Most of the air, 99% of it, is made of nitrogen and oxygen. The other 1% are gases like argon, neon, nitrous oxide, and carbon dioxide. And it's this gas that they're looking at as the culprit behind all this savage weather.
Superman had X-ray eyes. He could look at something you couldn't see with a normal set of eyes. So when we look at more carbon dioxide in the air, by color coding it, we see the planet as it couldn't be seen any other way.
CO2 data from those samples is represented by swirling clouds of red. And with this, we see something incredible. Earth breathing.
And the red is showing us that during winter, there's actually an excess of carbon dioxide, and that's because all the plants, the leaves have fallen and they're decaying and they're releasing carbon dioxide into the air. And as time goes on, and now we're in summer, and when we look at the blue, we're really seeing that the leaves have pulled so much carbon dioxide out of the air in the northern hemisphere that turned it blue.
But what this global sampling is showing us is that every year, Earth's breadth is growing more and more shallow.
So what you see here is plumes of high CO2 that come up from the land because of respiration. And this is that same picture now, but for 30 years, where we see that CO2 increases all over the Earth. Every single year, CO2 increases.
Since 1990, the amount of CO2 has grown by more than 8%. It doesn't sound like much, but because of it, we can see Earth is getting warmer.
We're changing the physics of the atmosphere. You change the physics of the atmosphere, there's going to be consequences.
And those consequences are floods, heat waves, and increasingly savage storms. But if we learn how these tiny chemical changes work, can we reverse course? Some folks are heading into the belly of a beast to find out.
We've lost contact with Teal 76. Oh God, we're going to DEFCON 2.
On the cusp of the Atlantic hurricane season, a crew from the Air Force Reserve's Weather Reconnaissance Squadron is flying into a monster. A 400-mile-wide tempest named Earl.
There's going to be some fairly intense weather out there, and we're going to essentially drive through most of it, straight through the center and into the eye of the storm.
With wind speeds of 135 miles an hour, Earl is churning in the Atlantic 350 miles east of Savannah, Georgia, and threatening the East Coast. Since its birth, satellites have been monitoring Earl. Onboard infrared cameras have been tracking temperatures in the storm. Other satellites beam down radar to create these 3D images, which reveal the inner structure of the storm. But there's one critical piece of data satellites can't collect.
Sometimes you have to go in and take a look at what's really going on. And the one thing that satellite imagery still doesn't do that we do is measure pressure. That's really the lifeblood of a hurricane.
To determine pressure, they'll fly into the storm and drop sophisticated remote sensors called sondes from the plane. Inside these cylinders, a GPS locator measures winds. Another sensor tracks heat. And most importantly, a barometer records air pressure. Once ejected, a small parachute opens to stabilize the descent. Every half second, the sonde relays measurements back to the plane. But they can't drop the sonde until they're in the eye of the storm.
Okay, guys, we're inbound. Let's watch the chatter. Okay, 5 miles to go. And up to 90 knots on this northeast side already. Here we go. It's going to get rough here right about now. 3 miles to go. 1 mile to the eye. And we're in it. It is nasty down below. Holy cow. I think that's pushing 70 knots, maybe more. You don't want to be down there.
Inside the eye, the crew drops a sonde, and the data starts streaming back.
I got 943. My first look at that sonde. Sounds right.
The numbers reveal Earl is starting to lose some of its punch. Pressure inside is rising, and the eye is beginning to fall apart.
It's not a real nice concentric eye like we thought it would be. Maybe get elongated, whatever. It's not open at the top. I think what we're figuring out is this thing is a little more disorganized and a little less strong than we thought it would be.
While the East Coast breathes a sigh of relief today, the next monster storm is on the way. Data from hurricanes like Earl is revealing a disturbing trend. the intensity of these storms is increasing. Another side effect of a changing planet. At the heart of all this change is a vital system, and Earth's most unique feature: life. From the highest mountains to the depths of the ocean, Earth teems with plants and animals. We know that changes in Earth's makeup affect life on it. But what about the reverse? Can life change the Earth?
You got those clippers on you? Thanks.
That's one of the questions oceanographer Jack Barth is exploring off the windswept coast of Oregon. Barth is here trying to solve a marine mystery. What's killing a growing 6,400 square mile stretch of ocean?
This piece of the ocean is called the Hecata Bank, as this is where the lowest oxygens are found up along the Oregon coast. So this, when oxygens go low enough and the creatures can't get enough oxygen out of the water, this is when they flee, and then it's so-called dead zone.
Dead zones are oceanic wastelands. Nearly devoid of oxygen, they drive organisms out and suffocate those too slow to flee.
As you go into one of these low oxygen zones or dead zones, you see dead animals, fish dead, being blown around in the currents. You see carcasses of crabs. These are the Dungeness crabs that are piled up on the sea floor.
Do one from the frame to this side.
Using sophisticated sensing technologies, Barth believes he's ID'd the culprit, an organism too small to be seen with the naked eye. Life is to this planet as blood is to the human body. It gives Earth its oxygen, cleanses the air of CO2, keeps the oceans from turning into acid, and acts as a thermostat by balancing the ratio of gases in the atmosphere. Understanding life as a critical system, you quickly see that some species carry more weight than others. Our species makes up just 0.2% of life's total weight. In terms of sheer weight, all the ants weigh as much as all of us. Tiny Antarctic krill outweigh us by a factor of 13. Plants by a factor of 3,800 to 1. But even these numbers pale in comparison to the invisible microbes and bacteria that may make up as much as 80% of life's total weight. These unseen creatures are everywhere. Just the microbes living inside the human body add nearly half a pound to a person's weight. In fact, there is so much microscopic life on the planet, it's estimated that if you took it all and laid it on the surface, it would cover Earth to a depth of 5 feet.
Good, Luke?
Yeah. It's one of these microbes that Jack Barth believes might be what's responsible for this stretch of dying ocean. It's a plant-like organism called phytoplankton.
Phytoplankton as primary producers, or the base of the food web.
Phytoplankton are one of the most important species on the planet. These plant-like creatures absorb billions of tons of carbon dioxide from the atmosphere and produce more than half of the world's oxygen. Every year, they explode in blooms so large, we can see them from space, fanning out across the sea. But ironically, it's this explosion of life that Barth believes is killing this stretch of ocean.
When you get that bloom, it's a great thing. On the other hand, when that plankton die off and they fall to the bottom, that's an organic mass of material that can then be decayed and pull the oxygen out of the water.
Every year, those blooms are getting bigger, and so are the dead zones. Where once they numbered just a few dozen, there are now more than 400 dead zones snaking their way around coastlines across the globe. Colored yellow and red for the most severely affected areas, we see them in Asia, off the coast of Japan and China, in Australia, and along the coastlines of North America.
It really is a change sweeping through the marine ecosystem here. Sometimes we use that forest fire analogy where it sweeps through an area and then you've got to rebuild that marine community.
Barth and his team are deploying a submersible sensor to the sea floor to sniff out clues as to why these phytoplankton blooms are getting bigger.
Let's go, Kim.
All right, we're gonna put them in then.
Everybody clear. All right. 10:30.
Using this sensor, Barth has discovered that currents of water moving from the deep ocean are growing larger. Called upwelling, these currents drag nutrients up from the seafloor.
It's just like fertilizing your garden in the spring. Wham, you get a bloom of plankton. Now, on the other hand, that same material, as it dies off and sinks to the bottom, that's the organic material that can decay and then rob the oxygen from the lower layers.
So if it's the blooms that deplete the oxygen and the deep water nutrients that feed the blooms, what's powering the increased upwelling?
In our system, the winds are very important to drive that upwelling. And if the winds change, it affects the upwelling in those lower layers.
Winds move warm surface water out to sea, and cold water from the bottom moves in to fill the space. So what's changing the winds?
Now, global warming can change the winds. We're seeing that on the planet where wind patterns change, wind intensities change. Likely heard about hurricane intensity. So that's the change in the atmosphere. So here on the Oregon coast, we're receiving these lower oxygen deep waters, and the winds seem to be changing. And those two together are shaping how that oxygen zone plays out.
Barth's study illustrates the complex relationship life, the atmosphere, and oceans share, and the transformative power life wields over the planet.
So we've never really had this information before, so we can now look at the ocean environment just like we do land environments and see how things are changing over time.
But when we take a closer look at how life can change Earth and the sometimes unintended consequences that go with it, we need to look at another species. Our own. Of the billions of species that have existed over the past 3.5 billion years, none's changed the planet faster or more dramatically than humans. Some believe a new age in Earth's history has dawned. The Anthropocene, the age of humans. But what does this new age mean to a living world? In the realm of ice and snow, the effects look something like a fever.
Yeah, this is a lot more ice in the water than it was the last time I was here. Like the chunks are bigger and there's a lot more volume.
At the foot of Alaska's Mendenhall Glacier, photographer James Baylog uses cameras to capture some of the most stunning visual data of Earth in flux.
These cameras are like my little pet robots. We set them up on these cliffs, and they're out there in these most abject conditions, and they just sit there, and their little eyes are working for you. Some of the cameras are exposed to minus 30, minus 40 degree Fahrenheit. We have winds that are constantly in excess of 100 miles an hour in certain locations. You know, this is pretty rough going for this equipment.
What Baylog has managed to capture is some of the most dramatic imagery of what happens when Earth runs a fever.
Climate change is kind of an abstraction to most people, but in these glaciers, it's a tangible thing where you can see these processes of massive change on the Earth happening right in front of your eyes.
Baylogs come to Mendenhall Glacier to retrieve data from 3 months of camera observation.
Okay, now let's have a look. There it is. There's pictures.
What his cameras reveal is a glacier in a near constant state of motion, breaking away, retreating, and flooding the lake with icebergs.
God, look at that. There's a lot more ice out there a little while ago.
What's going on now in ice fields like Mendenhall is something that's happened many times before. Earth's climate history is like a roller coaster. There were times when Earth was warmer and crocodiles basked on the shores of polar lakes. At other times, Earth was cooler and ice sheets a mile thick covered vast areas of the planet. But in the past, this ebb and flow was tied to things like changes in Earth's alignment and massive volcanic eruptions. Today, those changes are being forced and sped up by humans.
This is not natural variation. We are way beyond the realm of natural variation right now. It's very, very clear that these changes are taking place because of human impact on the environment.
For science, these images are priceless because it's information that can be cross-referenced with other data to better understand changes going on all over the world.
Scientists are taking these pictures and connecting the imagery to the climate, the warming, the daily variation in temperatures. All of that is tied to glacier behavior. A lot of things come together in these pictures, and different researchers are using them in different ways to tease out different parts of the story.
Piecing together the story of Earth, the organism, leads to some surprising revelations about our world. On the surface, the natural world appears random, frenzied, and chaotic. But look closer, and you'll see there are patterns. From the petals on a flower to the meandering track of a river. There's a geometry in the world around us. That geometry is called fractal. A fractal is a shape that's repeated at different scales. So that if you're looking at one part of the fractal, you're also seeing the whole. So what kind of insight do fractals give us into this living world?
Don't step in the plot. It's very easy to trample this vegetation.
Here in the Colorado backcountry, biologist Brian Enquist is using fractals to better understand how Earth breathes.
We're using fractal geometry to help us understand and hopefully predict the total amount of carbon dioxide that comes in and out of the ecosystem, effectively how the Earth breathes.
Enquist believes that by studying the geometry of individual plants, he can accurately gauge how much carbon dioxide is consumed by this environment.
If you were to invent CO2 goggles and put them on, what you would see is photosynthesis and respiration in plumes and waves all across this valley. CO2 coming in, CO2 coming out.
What Enquist is looking for is a pattern, a scaled relationship shared by a single plant or leaf and the environment it inhabits.
Within nature, we can identify patterns. Those patterns then can be described mathematically. And that's actually very powerful, because then if we have a pattern, we can then use that to more accurately predict and understand nature.
These natural patterns don't stop at plants. The same patterns can be found in all life on Earth, even within us. Take an X-ray of the human arm. It reveals a numeric design that's expressed throughout nature. One bone at the top connects to 2 bones in the forearm. Those connect to 8 bones in the wrist, which feed to 5 bones in the hand and 3 bones in each of the fingers. These numbers, 1, 2, 3, 5, and 8, are part of a famous mathematical set called the Fibonacci sequence. It's a series of numbers where each is the sum of the 2 numbers preceding it. Take these numbers and plot them on a graph, and what emerges is a spiral, whose arcing curve matches the pattern of a pine cone. That's also the same curve we see in a nautilus shell, and that's important.
A pattern is effectively the basis of how to do science. Scientists look for patterns in nature, and as biologists, we look for patterns in biology. Once we identify a pattern, that implies then potentially we can predict something about the world.
Just like the patterns of veins within a leaf mirror the branching pattern of the tree, a fractal is the same shape, just repeated at different scales.
A fractal implies self-similarity, and a self-similar pattern then is a pattern that is repeatable and observable at multiple different scales of observation.
Nature relies on this geometry because fractals allow it to create vast structures in an amazingly efficient way. It's how it packs 60,000 miles worth of veins and arteries into a human being. And it's how nature bundles 6-foot-long DNA strands into a tiny cell nucleus. In fact, if you took all the DNA inside one human and lined it up end to end, it would reach out past Pluto, 4 billion miles away. But fractals are at work in more than just organisms. They even permeate the environments those organisms inhabit. Look at an average tree in a forest, and the number and size of its branches closely reflects the number and size of trees in that forest.
If you look at an individual tree, and if you step back and if you look at an individual forest, what you'll actually find is a similar mathematical pattern.
It's that pattern that Enquist is trying to discover. Because with it, he'll have the data to say how much CO2 moves through this environment by looking at a single plant or even a leaf.
Be very gentle with this one.
But finding that pattern takes work. A lot of painstaking work.
If we have a closed, controlled little environment, we put our CO2 probe within the tent, and we can measure very quickly how fast then the plants scrub that miniature atmosphere of the CO2. So here, we're setting up the CO2 probe. Let's go ahead and lower the tent. Go. Take the chain off. So we're making a flux measurement right now. You can hear the little fans on the inside, and so we're mixing the air. These plants are scrubbing this little atmosphere of the CO2 that's inside the tent, and we can record how fast they're doing it.
448, 446.
Wow, it's really dropping fast.
443.
Every plant that was in the tent is then carefully measured,
82.7. 82.
cut, and bagged for transport back to the lab.
We're about to see an enormous amount of change that's going to be occurring within natural ecosystems, and so we want to know what's going to happen. And what we're trying to do is utilize these underlying mathematical truths about nature to try to help us predict what may happen in the future.
But do these patterns extend beyond the natural world? Can they be applied to our cities? To find out, Jeffrey West and his team of researchers look at data from cities on everything, from bank transactions to the length of electrical cables.
You look at every possible metric or characteristic that has been measured across multiple cities.
In these numbers, West is looking for a pattern similar to one that's universal in biology. Plot an animal's energy needs in relation to its weight, and an amazing pattern emerges. A mouse needs a lot of energy in relation to its size, has a fast heartbeat, but lives a brief life. An elephant is just the opposite. It needs less energy per pound, has a slow heartbeat, and lives a long life. Even more incredible is that all mammals scale at the same rate.
Each mammal that has ever existed on this planet, no matter how small or how big or what color they are, we are each some scaled version of one single mammal.
Is it possible that a similar scaling law could also apply to something non-biological, like a city?
It's quite fascinating what we found. Just as a blue whale is a scaled-up version of an elephant, which is a scaled-up version of a human being, it turns out that New York is indeed a scaled-up version of San Francisco, which is a scaled-up Boise, which is a scaled-up Santa Fe.
But there's an important exception. In nature, as an animal gets bigger, their energy needs per pound and pace of life slows down. The opposite is true of cities. The bigger they get, the more energy they need, and the faster everything moves.
If you look at spread of disease, rate of transactions, all of these increase as the city gets bigger. Even the pace of walking. The rate at which you walk amazingly increases systematically with city size.
But what makes West's research so incredible is that all cities scale at the same rate.
If you double a city size, what you discover is an extraordinarily simple rule that your wages will go up by about 15%, the number of police goes up by around 15%, the amount of crime goes up by 15%. There is this 15% rule that stretches across the whole spectrum of human activity.
Is this scaling pattern proof that seemingly separate issues like crime and disease are in some way linked? Is there some kind of natural order at work inside these concrete environments?
They seem to be extraordinarily interrelated and interconnected. All of these scale together with the same exponent. This cannot be an accident.
And if it's not an accident, and there is a natural order, even in cities, can problems like global climate change and crime be somehow related?
Just focusing on global warming, or understanding risk in the markets, or understanding problems of health and disease in Africa is dangerous. You need to have a much broader, integrated, holistic view. We need to understand how cities function to start to address these questions.
These interconnected relationships show that what we do has a direct impact on Earth. Now it seems like the planet is pushing back. As humans and Earth continue to evolve, the future of both hangs in the balance. The human species covers an enormous range. From the highest latitudes to the lowest, there's virtually no piece of dry land we don't inhabit. So what kind of information can we learn about Earth by looking at ourselves? Let's start by looking at where we live. Countries rise and fall based on the number of people living in them. But a different world emerges when we see where people are born. Looking at per capita data, we see even more. Here are death rates. And this is where people starve. So what do these maps tell us?
We use demographic data to know where the people are, first and foremost. But also, we need to know some of the characteristics of those people. For example, we need to look at the fertility rates. How rapidly is the population changing? So we get into properties of people.
Some researchers are using shifts in population, births, deaths, and rates of starvation to track changes on the planet. Shifts in atmospheric chemistry, for example, lead to changes in weather patterns, which can mean prolonged drought, less food, starvation, and death.
Climate change is much faster, and arguably the human populations are more sensitive because there are so many of us.
Starvation then also mirrors rates of disease, like tuberculosis, AIDS, and malaria. Those too can be linked to climatic changes. As the planet has warmed, researchers are now seeing malaria in places that were once cooler and therefore immune to the disease. Looking at a warming planet, we can change the data to see where greenhouse gases originate. We can even take that a step further to see how that tracks with modern-day luxuries, like cell phone use, internet access, and even fast food. What this changing map reveals is just how far outside the natural bounds some researchers believe our society has evolved.
50,000 years ago or so, our metabolic rate was 200 or 300 watts, even including our activity, and that was appropriate for our size. But now, we were using 11,000 watts.
It's not surprising that with 7 billion people and with all that we're doing, that we're changing our atmosphere. And we're changing it faster than it's changed probably in hundreds of thousands of years. It's a change that this planet hasn't seen and that we need to understand in order to prepare for.
And that's what these maps help us do: prepare. With them, we see trends, identify problems, and reveal how we as a species live on and with Earth.
Both the environment in which we live, the planet itself, and humanity determine our future. We live with that mixture all the time. We are both creatures of our site, where we are, and also of our situation, the context in which we live.
As the modern age brings this living planet into focus, perhaps the most significant discovery of all is that we are the planet, and the planet is us. That's why understanding this enormous organism we call home may be the most important thing we ever do.
It's a complicated world, but I think we're onto something that is showing us how nature works.
Though we may be changing the planet in ways it's never changed before, our ability to monitor our impacts gives us and Earth something it's never had: an awareness.
We've learned an immense amount, but in the years since, we've built better and better networks, and they allow us to look at our changing planet.
And that awareness may be what ensures that humanity isn't just one of Earth's failed experiments, but one of its most enduring triumphs.